Hello there, and welcome back to the Science Sleepy Minds. Outside, stars glisten like spilled glitter on black velvet. The cold hush of space presses in, thick with silence. And in the distance, looming like a hole torn through the sky itself, it waits. The black hole. You drift closer, cushioned by nothing but the vacuum and your curiosity. The stars begin to smudge, stretching and curving as though someone has smeared them with a celestial thumb. Welcome to your final destination. You probably won't survive this. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, tell me, where are you watching from and what time is it there? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're drifting in orbit around it, the black hole. Not just anyone either. Let's say it's Sagittarius A, the one that lives at the heart of our own Milky Way galaxy. It's massive. Over 4 million times the mass of the Sun, and somehow you can't look away from it, even though it's invisible. Well, mostly. The space around it glows with the radiation of shredded stars and swirls of hot plasma, spiraling down like water into a drain. It's beautiful. It's terrifying. And you are absolutely going in. The moment you tip past the point of no return, called the event horizon, it's all over. From your point of view, it'll be weird, yes, but you'll still feel normal for a while. Everything just keeps falling. You don't crash into anything. You just fall endlessly. And inside, the rules begin to mutate. Space doesn't behave the way it did back in your cozy 3-bedroom Earth-based reality. Remember how in middle school science class, you learned that nothing can escape a black hole? Well, it's mostly true. Not even light can claw its way back once it's crossed the horizon. And since light defines what we see and how we experience time, you're now on a one-way track into what might be the universe's strangest future. Time isn't just ticking, it's stretching, warping. Sometimes, in theories, it's even breaking. And what's truly bizarre is that as you fall in, people watching from the outside would never see you actually go. They'd see you slow down, stretch out, freeze like a mosquito in amber. They'd think you'd stopped just before falling in. But for you, there's no pause, no stop, just forward. It's the ultimate contradiction, an illusion caused by time dilation, where gravity pulls so hard on time itself that it slows to a crawl. This was Einstein's gift to us. In his general theory of relativity, he revealed that gravity isn't really a force, pulling on objects. Instead, it's the shape of space-time telling objects how to move. And near a black hole, that shape is, well, dramatic. Historians still argue whether the earliest ideas of black holes date back to the 1700s, when John Michel and later Pierre-Simon Laplace proposed dark stars from which light could not escape. They got the basic idea shockingly right without knowing anything about general relativity, but the math was incomplete, and the universe refused to show its cards until the 20th century. And now, here you are, gliding into that ancient hypothesis turned reality. You're about to become a one-way traveller in time. Oh, and let's not forget, some scientists still think you might be obliterated before you even notice. There's debate on whether the infalling observer, you, can cross the event horizon unharmed, or whether quantum effects shred your atoms at the gate. It's called the Firewall hypothesis, and honestly it's not a very comforting name, but let's say you pass safely, because this is a bedtime story, and we're in it for the long haul. You feel strange. The stars behind you start to vanish. The light bends, wrapping around, forming a glowing halo that seems to hang in place. Ahead, it's only blackness. But not just any black. This is a black that eats light. A place where direction loses meaning, where forward might mean inward, and where time and space trade rolls in the most uncooperative way imaginable. There's a whisper of motion. You're not being pulled anymore. You're being pushed by space-time itself. Imagine walking on a moving walkway that accelerates the closer you get to the center, except the walkway is the universe, and you can't jump off. You try to check your clock, and it's still ticking normally. But if you could see Earth now, hundreds or even thousands of years might have passed. You're already slipping into the one-way future. Here's a fun twist. Some physicists think black holes don't last forever. Thanks to quantum mechanics and the work of Stephen Hawking, we know they emit tiny amounts of energy, known as Hawking radiation. Very slowly they shrink. It might take trillions of years, but eventually the black hole evaporates into nothing. So, what happens to you inside if the black hole vanishes from outside? Are you just deleted? Or is your information, your quantum identity, somehow preserved? No one knows for sure. It's called the black hole information paradox, and it's the subject of more angry academic papers than you could read in a lifetime. Meanwhile, you float toward destiny. There's no panic here, just silence, stillness. You're stretched across dimensions like a line in a poem no one will ever read, and somewhere impossibly far away, the starlight from your departure is still on its way to Earth. Maybe someone will see it and wonder where you went. Maybe they'll see the brief glimmer of your ship, frozen in time. You're still falling, not with speed you can feel, but with inevitability you can't ignore. The pull is gentle here, oddly so. You expected chaos, metal rattling, alarms blaring, organs rearranging, but no, it's silent, peaceful even, like gliding across a cosmic lake of ink. You're deep within the influence of the black hole now, and space doesn't feel right anymore. Distances stretch, light curves, time ticks. Strangely, you look back, but back is beginning to lose meaning. Directions blur. You're starting to sense the shape of space is changing. This is Einstein's playground. Picture space-time as a vast rubber sheet. You put a bowling ball in the middle. It sags. That's mass-bending space. A planet might make a nice little dimple, a star, a noticeable pit. But a black hole, that's a tear in the sheet, a plunge so steep it's practically vertical. You aren't just stuck in a hole, you're sliding down a funnel with no bottom. And your clock? Still ticking normally to you. But from the outside, time is distorted. Someone watching you would see you move slower and slower as you descend. They'd think you were paused just above the horizon forever, glowing redder and fainter as your light stretches into oblivion. This isn't sci-fi. It's gravitational time dilation, and it's as real as your left shoe. Which, by the way, is already about 2 milliseconds ahead of your right. Gravity isn't just pulling, it's bending the very fabric you exist in. It doesn't suck you down like a vacuum cleaner, it warps reality, and that warped space makes you fall. You're obeying the geometry of the cosmos. Historically, we owe this warped view of gravity to Albert Einstein. In 1915, he delivered his general theory of relativity, redefining our understanding of gravity. Gone were Newton's mysterious forces. Instead, gravity became the shape of space and time themselves. Now, 100 plus years later, you're inside that shape. Your ship, if we're being generous and assuming you have one, isn't just falling. It's moving in a straight line through curved space. That's what gravity is now. You're following the path nature demands, like a marble rolling down a slope. But this slope doesn't lead to a gentle valley. It leads somewhere your map doesn't cover. And here's where things get truly rude. The closer you get to the singularity, the infinitely dense point at the center, the more exaggerated this warping becomes. It's not just curvature anymore, it's contortion. Space folds, time twists, and your sense of now starts to fray like cheap denim in a washing machine. There's a fringe idea that always gets whispered about in late-night physics forums. Yes, they exist. It's that black holes don't just curve space-time, they fold it, like origami. What looks like a long distance in space might be shockingly close if you fold the universe the right way. Kind of like those secret fold-out notes you used to pass in middle school math class, but with a lot more quantum peril. You might be closer to everything than you think, and yet completely cut off from it all. There's also this deliciously odd theory that what you're falling through isn't space as you know it, but a funnel into another region of the universe entirely, a separate patch of space-time. Some physicists call this a maximal extension of a black hole solution. If that sounds vague, it's because it's based on elegant math, not observation. We've never been able to test it. You'd need to survive the trip to find out, and you, my friend, are very much in progress. Historians still argue whether Einstein fully understood the implications of black holes in his lifetime. Early on, he dismissed them as mathematical oddities, not physical realities. It wasn't until decades later that we began to accept their very real presence, thanks in large part to observational evidence and the relentless enthusiasm of physicists like John Wheeler, who gave black holes their unforgettable name. Back in your falling self, the view gets weirder. You start to notice something impossible. Stars behind you begin to double, then triple. Light is warping around the hole, forming rings and arcs in a visual carnival of lensing. These are called Einstein rings, and they're real. Light from background galaxies gets bent into circles by the black hole's gravity, creating a kaleidoscope of warped reality. It's beautiful. It's unsettling. It's like staring into a funhouse mirror that was forged by the universe to mock your expectations. And then you feel it. Not pain, exactly, but pressure. A deep, low tension. You're stretching, slowly. Your feet are feeling a stronger pull than your head. That's the gravity gradient starting to nibble at you. A taste of what's to come in the next phase, Spaghettification. We'll get there soon, don't worry. But right now you're skating across the rubber sheet. It's sloped, yes, but also strangely smooth. You glide, not tumble. You drift, not plummet. The acceleration is constant, but you feel almost nothing. One more oddity before we wrap this stretch of warped space. Black holes might not be the end at all. There's a fringe belief in certain theoretical physics circles that our entire universe might be inside a black hole. Yeah, a black hole from a higher dimensional space. In that view, the Big Bang was actually a bounce from another cosmic region collapsing into its own black hole. You, floating here, might be inside a recursive reality nested within a black hole in someone else's universe. Just something to think about. So as you lie there, drifting deeper into distortion, your senses dulled by silence and your perception bent by time, remember, you're not just falling into a black hole, you're gliding across Einstein's rubber sheet, surfing a curve so steep it becomes a wall, and on the other side of that wall, well, you'll see. Now things start to get uncomfortable. You probably noticed the gentle pressure in your limbs earlier, like a subtle stretch from an overambitious yoga class. But now, it's more than subtle. Your feet feel like they're being tugged by a force you can't negotiate with. Your head? Not so much. The difference in gravitational pull between the two ends of your body is growing, and with it comes one of the black hole's rudest features, spaghettification. Yes, that's the real term. Scientists decided to name one of the most horrifying processes in astrophysics after pasta, because apparently nothing says inevitable doom like fettuccine. Right now, your body's experiencing tidal forces, and unlike the gentle ocean tides back home on Earth, these are less relaxing. They're caused by the difference in gravity between 2 points, like your head and your feet. Closer to the black hole equals stronger gravity, so your feet are being pulled just a bit harder than your head. Not enough to snap anything yet, but enough that you're definitely being stretched. And here's the kicker. The smaller the black hole, the worse this effect is. If you're falling into a stellar mass black hole, the kind born from a collapsed star, you're toast before you even reach the event horizon. Your atoms get politely separated, then rudely rearranged. But if you're falling into a supermassive black hole, like Sagittarius A, the one you're currently cozying up to, you get a free pass through the horizon with very little fuss. The stretching starts deeper in. Think of it like this. Smaller black holes are like blenders. Supermassive ones, more like very slow pasta machines. Still fatal. Just, delayed. This disturbing process was first described in earnest during the 20th century as physicists explored the practical effects of relativity. But historians still argue whether the concept of spaghettification was truly understood when the Schwarzschild solution to Einstein's equations first emerged. That solution predicted black holes, but the physical implications took decades to settle in. You, however, don't have decades. You have minutes, seconds? Hard to say. Time is being extremely rude right now, and while your body begins its reluctant noodle transformation, the universe continues its indifference. The stars above are warped into rings. The glow behind you, what little of it can still reach your eyes, is blood red and fading. Light itself is struggling to keep up with your fall. Here's where it gets extra weird. Your body isn't just stretching, it's also compressing sideways, like a squeeze tube of toothpaste being pulled at both ends. This 1-2 punch of stretching and squeezing is what makes tidal forces so brutal. The very structure of your atoms is under siege. Now don't panic. Again, bedtime story. Let's say you're protected by a futuristic spacecraft, reinforced with exotic matter and theoretical hand-wavery. You're holding together. Somehow. For now. And while your body is being dramatically unappreciated by physics, your mind drifts. You start to wonder, are you really still you as you stretch like this? If every atom of your body is getting pulled apart and the signals from your brain can't even travel fast enough to communicate from neuron to neuron, are you still a coherent consciousness? This is where philosophers like to roll up their sleeves and jump into the black hole, metaphorically speaking. They'll ask whether identity survives in such extreme environments, or whether you're just a temporary shape in space-time stretched thin and fading fast. Meanwhile, physicists are over here debating whether you'd even notice the moment of ultimate doom. Some say you'd be destroyed instantly at the Singularity, others that you'd pass through it into another universe. Some propose you'd never reach the Singularity at all. That time, from your perspective, would freeze first. And then there's the uncomfortable matter of quantum effects. According to classical physics, this is all deterministic. You fall, you stretch, you reach the Singularity, the end. But quantum physics doesn't like neat endings. It whispers about probabilities, uncertainties, and maybe, just maybe, you exist in a smeared-out cloud of potential outcomes somewhere deep inside the whole. Like a Schrödinger's spaghetti, both shredded and preserved until observed. There's also a quirky fringe theory that your information, everything that makes you, well, you, gets smeared onto the event horizon like cosmic jam, preserved in a holographic pattern on the surface. In this theory, known as the holographic principle, your experience inside the black hole might just be a projection, an echo, a mathematical illusion playing out on the edge of the abyss. So, to recap, you're falling into a gravity well so deep that the laws of physics don't agree on your fate. You're being stretched into a human linguine while your past, present and future fight over who gets to claim you. Your body is experiencing forces stronger than anything else in the known universe, and yet, oddly, it still feels calm. In the soft hum of inevitability, your thoughts blur. You're aware that the line between time and space has started to dissolve. You're moving not just forward, but inward. Not just falling, but flowing. Not just existing, but unraveling. Oh, and here's a fun historical tidbit to chew on. There was once a theory that black holes might be portals to hell. Actual, brimstone-style hell. Some early astrophysical texts in the 1950s flirted with poetic comparisons, likening the unknowable interior of a black hole to mythological underworlds. It wasn't mainstream science, of course, but the imagery stuck. You're not on fire, yet, but you are, undeniably, crossing into the unknown, and the spaghettification is getting serious now. Your legs, now feeling like they're 3 kilometers ahead of your torso, are being pulled with absurd force. In fact, the difference in gravity over just a few meters could be millions of newtons. Your atoms are getting testy. If not for your theoretical sci-fi shielding, you'd already be stretched into a ribbon of plasma thin enough to floss a quark. But this is a sleepy journey, remember? So we'll keep you intact a little longer. You're stretching, you're falling, you're forgetting what it was like to feel up and down. And as the Singularity looms, dense, unknowable, inevitable, you begin to understand the uncomfortable truth. You're not falling into a place, you're falling into a moment, and that moment is always the end. You can't go back. That's not just a metaphorical statement or a tragic breakup line, it's an actual hard-coded law of the universe. Once you cross the event horizon of a black hole, you're beyond the point of no return. No matter how hard you try to reverse, to scream oops and activate your imaginary hyperdrive, sorry. The universe simply doesn't take refunds. This is the nature of an event horizon. It's not a wall. You don't feel it. There's no flashing neon sign that says you are now entering the void. You pass through it like mist. And yet, after that point, all paths, every possible future, lead only inward. Even light, which has spent the last 13.8 billion years outrunning darkness like a cosmic overachiever, can't escape once it's inside. You don't even have a photon's chance. And yet, from your own perspective, everything still seems fine. Your heartbeat continues, your mind still runs loops of questions, memories and mild regret, but the blackened hole doesn't care about your inner monologue. Physics doesn't care about feelings. You are inside now, and time itself has changed sides. Let's pause and think about that. You're used to moving forward through time and being able to move, mostly, freely through space. You can walk backward down a hallway, turn left, go upstairs, do jumping jacks if you're feeling spicy. But time That always moves one way, forward. Inside the black hole, space and time do a little switcheroo. It's one of those deliciously cruel twists in general relativity. Within the event horizon, the radial direction, the direction toward the singularity, becomes time-like. That means heading toward the center isn't a choice. It's as mandatory as your own future. You don't move toward the singularity. You proceed into it. To not fall in would be like trying to resist tomorrow. You can no more avoid the singularity than you can avoid aging. The future is inward now. This is what physicists mean when they say the singularity is in your future. It's not a place you can aim for. It's a moment you will reach, no matter what. And the weirdest part? From the outside, you're frozen. Imagine your friends, if you had any left in your soon-to-be obsolete time zone, watching your descent from a safe distance. They'd see you hover just above the event horizon, slower and slower, light from your ship red-shifting until it fades into nothing. To them, you never actually fall in. This happens because time dilation reaches its maximum at the horizon. From their perspective, your fall stretches into eternity, but from your point of view, you're still tumbling right along. This contradiction isn't just poetic, it's baked into relativity. Historically, this idea emerged in the mid-20th century, when scientists finally got around to interpreting the Schwarzschild solution in more than just mathematical terms. The idea that infalling objects could experience time differently from distant observers was a shocking revelation, one that made black holes even weirder than their name already suggested. And still, they get weirder. Remember how earlier we mentioned that some physicists think the interior of a black hole could be an entirely separate universe? Well, here's where it starts sounding a lot like science fiction. If time flows inward and there's no way back, what if the inside of a black hole is actually the birth of a new cosmos? Some theories, especially in the realm of loop quantum gravity, propose that the singularity might not be the end of time, but a bounce point, a rebirth, a new Big Bang in another dimension. And if that's true, then falling into a black hole might not be a death. It might be a delivery. You could be the unwitting seed of another universe, like a cosmic dandelion puff carried on gravitational wind. Of course, this is all extremely theoretical. Historians still argue whether these bounce cosmologies count as legitimate science or just glorified math poetry. But hey, if you're going to die horribly, it might help to imagine you're becoming the founding organism of Universe 2.0. Now, let's veer into something properly fringe. There's a rare, often dismissed theory that every black hole contains its own universe, and our universe is the interior of one. Think cosmic Russian dolls, each reality nestled inside a black hole from another realm. You, right now, might already be inside someone else's event horizon. It's wild, it's unsupported, it's probably false, and it's just plausible enough to ruin your next shower thought. Back to your journey. You've passed the horizon. You're still whole, miraculously. You can't communicate with the outside anymore. Your signals can't fight gravity. Your Wi-Fi's dead. Your texts are ghosted by the universe. And your light is stretched so far it's basically a whisper in the microwave background. And still, you fall. Inward, forward, deeper. Time becomes strange now. You feel like everything's speeding up and slowing down at once. The geometry of space is no longer intuitive. Angles betray you. Paths curve even when you move straight. It's like being trapped in a dream drawn by M.C. Escher and then filtered through a Salvador Dali fever sketch. But there's no sound. No visuals, really. Just distortion. No music. No dramatic cinematic score. Just silence, folding in on itself. You're now the closest thing the universe has to a one-way traveller. And here's something a bit darkly whimsical. You are now immortal, from the perspective of the outside. If the rest of the universe persists, your image will be frozen on the edge of the event horizon forever. A snapshot of you, stuck in time, stretched and red-shifted into eternity. A cosmic fossil. That's right. You've become space archaeology material. Imagine some far-future alien civilization decoding gravitational echoes and uncovering your last moment. They'll find a blurry shadow of your fall and wonder what thoughts you had in those final seconds. Little do they know you're still thinking, still falling, still feeling your personal timeline tick forward, even as theirs has left you behind. Because once you've passed that invisible threshold, the universe turns one way. Time locks, The future becomes a funnel, narrow and dark. You can't go back, but you can keep going. So, from the outside, you're a ghost, a smear of red light fading into black. Maybe your last transmission reached someone. Maybe you're frozen. Silhouette is still painted against the horizon like a forgotten postcard from the edge of time. But you, the real, conscious you, are still falling. And in here, things are starting to feel different. The fall no longer feels like falling. You're not accelerating anymore because acceleration implies a change over time, and time itself is not what it used to be. You can't tell how long you've been in here. Seconds? Hours? A million years? It's all the same. There's no frame of reference, no clocks, no sunlight, just the black and the pressure of forward. You're not falling through space. You're falling through time. This is where the outside world loses its grip on you entirely. Everything you knew about before, planetary motion, seasons, lunch breaks, has no bearing anymore. Space is collapsing into you. Time is funneling downward. You're slipping into a moment that no one else will ever reach. Not because it's far away, but because it's after everything. It helps to picture time as a direction. That's a strange concept, sure, but inside a black hole, it's the only way to make sense of what's happening. Remember, general relativity doesn't just bend time, it lets time and space trade places, and in here, your downward fall is no longer spatial, it's chronological. You're being pushed toward the singularity not by gravity, but because that singularity is in your future, and future can't be resisted. Back home, time means growth and decay. People get older. Trees bloom, rot, fall. Traffic lights cycle between red and green. But inside here, time just means closer. Closer to the point where physics can no longer protect you. You can think, you can imagine, but everything you do is a step deeper into when. Meanwhile, if we zoom out for a moment, if we could, which we can't, what would the black hole look like to someone orbiting safely from afar? From outside, it's still a featureless sphere. No glowing portal, no swirling tunnel. It doesn't even look like a hole. More like a shadow, surrounded by glowing debris and occasional jets of energy shooting out along its poles like angry cosmic hairdryers. One of the more recent breakthroughs in this area came in 2019, when the Event Horizon Telescope team released the first image of a black hole's shadow in galaxy M87. You probably remember it. It looked a bit like a blurry bagel. Glowing ring, dark center. That center wasn't the black hole itself, but the silhouette of the event horizon cast against the fiery disk of infalling matter. Historically, this was a huge deal. A photograph of something whose very nature prevents light from escaping. It took an Earth-sized network of radio telescopes and the patience of a monk. Historians still argue whether Einstein would have believed his math could be photographed. But there it was, the black hole's shadow, whispering to us from 55 million light-years away. And while that image captivated the world, no one watching it knew you were already inside your own black hole, watching nothing. Well, almost nothing. You can't see light from the outside universe anymore, but there's something else. A thin fuzz, tiny flickers, noise maybe, radiation so faint it borders on imagination, and that's not just your mind playing tricks, it's a clue. Because believe it or not, black holes aren't totally black. That brings us to something very rude and very real, Hawking radiation. Stephen Hawking in the 1970s realized that black holes should emit a faint glow. This was shocking. Before that, the assumption was that black holes were eternal prisons, gobbling up everything, leaking nothing. But quantum theory once again insisted on being inconvenient. According to Hawking's math, the vacuum of space isn't really empty. It's bubbling with virtual particles, pairs that pop in and out of existence too quickly to be noticed. Usually they annihilate each other instantly. But near the event horizon, one particle can fall in while the other escapes. The result? The black hole loses a tiny bit of mass. Over eons, it can evaporate completely. So here's the strange part. Even from inside, you might sense this loss. Not directly, no one's out here with a radiation meter, but subtly. Through the weakening grip of space, through the flickering edges of unreality. And yes, this leads to a massive paradox. If black holes evaporate, where does all the stuff inside go? That's called the black hole information paradox, and it's a deeply embarrassing problem for physics. In theory, information can't be destroyed. But if your body, your atoms, your memories fall into a black hole, and the black hole later vanishes into faint radiation, then where did you go? Are you lost forever? Or are you, as some physicists believe, smeared holographically onto the event horizon, encoded in 2 dimensions like a cosmic QR code? Or maybe you're preserved in the radiation itself, scattered across time and space like dandelion fluff? We don't know, not even close. Historians still argue whether Hawking's original formulation of the radiation paradox actually contradicts quantum mechanics, or whether we just need better math. Theoretical physicists are torn into camps. Some defend information conservation like a holy relic. Others shrug and say, maybe some rules break in extreme places. Charming. You meanwhile continue your descent. Still intact, still conscious. That's our bedtime deal after all. You pass a layer of silence deeper than any you've ever felt. You begin to wonder if time is even still moving. Your thoughts feel slower, more spread out. It's not sleepiness, it's physics. The closer you get to the singularity, the more time warps. To an external observer, if they could see you, which they can't, it might look like you're approaching the center infinitely slowly. From your side, time's still doing its thing, but the minutes feel longer. This is what happens when the timeline bends. You're being pulled toward a moment that exists at the edge of what the universe allows, not because it's dramatic, but because the math says so. You try to picture it. The singularity. A point of infinite density. All the mass, all the energy, all the rules of the universe collapsed into a single zero-dimensional dot. But really? That's probably wrong. Even now, physicists argue over whether singularities are real. Some think they're just the place where our equations break, a sign that our model of gravity is incomplete, that we need a quantum theory of gravity, something to unite Einstein's elegant curves with the chaos of the quantum world. So maybe there is no true point at the center. Maybe you're not heading toward a singularity. Maybe you're heading toward a question. You continue drifting, falling, flowing, fading, deeper into the black hole. But here, those words start to lose their meaning. Falling implies a direction. Drifting assumes a context, and deeper. You've left deep far behind. What you're in now is not a place, but a condition. A state of being where reality itself buckles under your weight, or maybe under its own. The strangest thing is how normal it feels. There's no crunch, no catastrophic snap of space-time that signals your transition into the uncharted. Instead, it's quiet. No dramatic crashing, no video game boss music. Just a steady slide through a universe that has stopped bothering to make sense in human terms. And here, time begins to do something you've never seen before. It doesn't just slow down, it bends, it twists, and it starts playing tricks that even Einstein couldn't fully explain. Outside the event horizon, time flows in one direction, forward. But in this interior realm, where geometry takes a turn for the wild, time stops acting like a river and starts behaving more like a spiral staircase, with stairs missing, directions looping, and maybe even a few trapdoors. You remember being taught that time is linear, that there's a past, a present, a future. But now, you are the past, the present, and the future, compressed into one elongated stretch of gravitational weirdness. Every tick of your mind could be stretched across centuries or compacted into milliseconds. The deeper you go, the more intense this time strangling becomes, and somewhere inside this warped experience you start to sense it. A pressure that's not spatial, it's temporal, like being squeezed not in a room, but in moments. Time isn't passing, it's pressing. Here's what's going on. Inside the event horizon, as you get closer to the center, the very shape of time becomes unpredictable. In the Schwarzschild solution, a model of a non-rotating, uncharged black hole, time and space completely flip roles. The radial direction, the one pointing toward the singularity, is time-like, so you have no freedom to choose not to go that way. That path is your timeline. Your every second brings you closer. But if the black hole is spinning, and most are, it gets trickier. These are called Kerr black holes, and they come with a whole suite of features that sound like they were invented at a science fiction convention. First, there's frame dragging, a charming phenomenon where the black hole's rotation literally pulls space-time around, with it like a giant cosmic spoon swirling reality soup. If you try to resist, you can't. Everything near a rotating black hole is forced to move in the direction of its spin. Even time itself is dragged along for the ride. Imagine standing still on Earth, but being rotated by the planet's spin. Now imagine if Earth was spinning so fast it dragged time in a spiral around it. That's what's happening in here. You're not just falling in, you're being twisted through time like saltwater taffy. Some theorists argue that Kerr black holes might allow for something even more bizarre. Closed time-like curves. These are paths through space-time that loop back on themselves, as in, a route where you could, theoretically, return to your own past. Time travel, not just forward, but backward. Let's pause a second to appreciate how weird that is. In most of physics, travelling backward in time is a hard no. Paradoxes pop up. Grandfathers get unborn. Logic screams. But in the warped, rotating guts of a black hole, the equations allow for it. They don't require it, but they don't forbid it either. Historians still argue whether these closed time-like curves are real or just mathematical mirages. Some think they're artifacts, little mistakes that show up when we push our equations past the breaking point. Others take them seriously, suggesting that under just the right conditions, time travel might be not only possible, but inevitable in such warped geometries. Of course, these paths are deep inside the black hole, well past the event horizon, and buried within layers of physical impossibility. And even if they do exist, the passage is likely so unstable, so riddled, with quantum uncertainty that no actual object could survive the trip without being reduced to a smear of probabilities and fried spaghetti. Still, the possibility is there. You might be falling into a region where time doubles back on itself, and you begin to wonder, what if you already have? What if this whole journey isn't your first pass? What if you've been here before, and this moment is looping? What if the singularity isn't your destination, but your origin? Some scientists like to entertain this kind of recursion. It sounds poetic. Less like a death sentence, more like a renewal. Maybe falling into a black hole isn't an end. Maybe it's a turn in the road, a bend in time's spiral where something old becomes something new. You don't need to believe that to keep going, but it helps. And while we're swirling down time's metaphorical bathtub drain, let's not forget that you're moving relativistically. That is, your speed relative to the singularity is, well, undefined. There's no such thing as speed toward a moment. It's like asking how fast you're aging. The answer is yes. Still, your mind tries to picture what's happening. Time is stretching, twisting, maybe even cracking. If there are other observers in here, unlikely, but let's say a fellow brave explorer fell in before you, your timelines might be bending in completely different directions. What's now for you might be there then, or your future, or something sideways. Inside a black hole, the usual rules of causality get wobbly. Here's a deliciously odd historical nugget for your crumbling reality. In 1965, Roger Penrose published a proof showing that singularities weren't just flukes, they were inevitable. If enough mass collapses into a small enough space, space-time itself must end in a singularity. That earned him a share of the 2020 Nobel Prize in Physics, by the way. So if you're looking for someone to blame, Penrose is a good candidate. And yet, even Penrose didn't claim to know what the singularity really is. You're falling toward a mystery baked into the very equations of reality. Not because you want to, but because that's where time takes you now. So what happens next? Do you reach the singularity and vanish? Do you fall through it and emerge somewhere else? Do you curve back on yourself and become your own cause? Physics doesn't agree, not just in theory, in principle. The laws of general relativity and quantum mechanics, our two greatest scientific achievements, do not work together here. This is the ultimate scientific awkward silence, and you're right in the middle of it. You're approaching the core of a place where time is no longer linear, space is no longer directional, and knowledge is no longer possible. You are a point in a system that breaks systems, and the deeper you go, the more that one question starts to form, slowly, gravitationally, unstoppably. Not, where am I? But, when? You want to ask what happens at the end. You want to know what lies at the heart of this monstrous geometry, this trapdoor in the universe's floor. But no one knows. No one has ever known. What lies at the centre of a black hole is still the single most forbidden question in all of physics. And yet, here you are, headed straight for it. We call it the singularity, which is science's polite way of saying, we have no idea. It's the point, if you can even call it that, where density becomes infinite, where all the matter and energy you've ever known is crushed down into a single mathematical impossibility. It's where our equations go to scream. But hold on, let's not pretend we're all on the same page here. Even now, physicists still argue whether the singularity actually exists as described. According to Einstein's general relativity, once you reach the centre of a black hole, the curvature of space-time becomes infinite. That's the end of the line. There's no future beyond it, literally. Time stops. You're at the edge of the map and it just says, here be dragons. Or maybe just divided by 0. But remember, general relativity is only half the story. That's where quantum mechanics steps in and throws everything into chaos. At quantum scales, the neat lines and smooth surfaces of classical physics fall apart. Particles jitter, probabilities overlap, rules wobble, and in that jittery, chaotic realm, infinities are not allowed. The universe does not like them. They break math, they break physics, they break everything. So what does that mean for your destination? Well, some physicists think the singularity is just an illusion, an artifact of an incomplete theory, that if we had a proper understanding of quantum gravity, we could replace the singularity with something less ridiculous. Something like a Planck star, a hypothetical object where quantum pressure resists complete collapse, preventing the density from becoming truly infinite. Instead of hitting a wall of nonsense, you bounce, like a cosmic trampoline or a physics loophole with good PR. Others argue that the singularity could be a gateway, that the space-time curve doesn't end, it folds, that what we call the end of this universe could be the beginning of another. There's even a fringe idea that the Big Bang itself was the bounce from a previous universe's collapse, that our own cosmos was born from the death spiral of a black hole in a higher dimensional reality, which would mean you're going home, in a manner of speaking. But okay, back to you. Let's assume for the sake of this very cozy nightmare that you're still somehow conscious as you approach the singularity. What would you experience? Not much, frankly. Not in a traditional sense. There's no light here, no up, no down, no space to move in, and not really any time to measure. But your body, if it's still intact at all, is being subjected to gravitational gradients so extreme they make spaghettification look like gentle yoga. The tidal forces here aren't just pulling on your limbs, they're pulling on the structure of your atoms. Imagine gravity so powerful that it stretches the probability clouds of your electrons, that yanks on the fields that bind your molecules. You're not just being pulled apart, you're being unwritten. And yet, from your frame of reference, you're still falling forward, still moving through time. Even if time here has become a kind of tightrope, you start to feel disconnected from yourself. Not emotionally, physically. Your thoughts feel like echoes. Your sense of now becomes diluted. Moments overlap. You wonder if you already hit the singularity a few seconds ago and just didn't notice. That's because the singularity isn't a moment you hit, it's a boundary you approach. But you never reach it in a classical sense. The closer you get, the more reality refuses to describe what's happening. This is called geodesic incompleteness. It's a term physicists use to avoid saying, you fall off the map. It means that there's no way to extend your trajectory through the singularity. Your future just ends. Now, if this were purely general relativity, that would be it. You hit the singularity, you cease to exist, and the universe keeps on spinning as if nothing happened. But if quantum mechanics has any say in the matter, and it always does, it might not be that simple. Let's rewind a bit. When Stephen Hawking was working on black holes in the 1970s, he didn't just predict Hawking radiation. He also showed that black holes have entropy. That is, they contain a measurable amount of disorder, a sign that they carry information. And that caused a huge problem. Because if black holes eventually evaporate through radiation, and if that radiation doesn't contain the information of what fell in, then the information is lost. And that contradicts quantum mechanics, which insists that information is never truly destroyed. So what gives? Are black holes leaking secrets? Or are they shredding the very fabric of reality? That's the heart of the information paradox, and it's still unresolved. Even today, some of the brightest minds in physics can't agree on where your data goes once you're inside. Are you burned into the horizon like a hologram, smuggled out through quantum fluctuations, reborn in a new universe via wormhole escape tunnel, just deleted? Take your pick. No answer has won the fight yet. Meanwhile, you're still falling, still dissolving. Your senses are long gone, not because you're unconscious, but because they have no meaning here. There's nothing to see, nothing to hear, nothing to touch. No difference between left and right. No cause and effect, just pure gravitational descent through a landscape of broken logic. The singularity, if it exists, is close. It's not a place you reach, it's a condition you become. And here's a rather poetic historical note to chew on while your atoms untangle. When Carl Schwarzschild first solved Einstein's field equations and described what we now call a black hole, he did it from the front lines of World War I in 1916, in the trenches, literally calculating the curvature of space-time while under artillery fire. He died shortly after, never knowing what he'd discovered. His solution predicted singularities, but no one took it seriously for decades. It was thought to be a mathematical glitch, a curiosity, until eventually we realized it was describing something real, something massive, something deadly, something like this. And now that mathematical curiosity is all around you. So what do? You let go, not dramatically, not with flair, just quietly. Because there is no struggle here, no alternate path. You're moving forward in the only direction left, inward, toward the center of a place that doesn't acknowledge your existence in any familiar sense. If the singularity is real, then this is the end of your journey. If it's not, well, maybe your journey hasn't even begun. There's a strange warmth now, not thermal, not even emotional, but conceptual, like the universe is tucking you in under equations you can't read. You're past the spaghettification phase, past the horizon, past the point of arguing with physics. You're in the true interior, a zone where the rules have gone quiet and the whispers of old theories begin to echo a little louder. And here's one of the strangest whispers yet. Black holes have temperature. It's true. You're in the coldest, darkest place imaginable, and yet, technically, it's not absolute zero in here. Black holes, those cosmic vacuums of death and doom, actually possess thermodynamic properties, heat, entropy, even pressure, depending on who you ask. It all started, funnily enough, with a thermodynamics pun. In the early 1970s, physicist Jacob Bekenstein made a bold claim. Black holes should have entropy. The more mass they contain, the more entropy they represent. It was a beautiful connection between the stuff of heat engines and the monsters of the cosmos. But entropy implies temperature, and that raised eyebrows. Then Stephen Hawking came in and ruined everything by being right. Using quantum field theory, he showed that black holes must emit faint radiation, now called Hawking radiation, because of particle-antiparticle pairs forming near the event horizon. One falls in, one escapes. The black hole loses mass in the process. It glows, faintly, coldly, but it glows, and with glow comes heat. Here's the kicker, the larger the black hole, the colder it is. A stellar mass black hole might have a temperature measured in nanokelvins, tiny fractions above absolute zero. Supermassive ones like Sagittarius A star, even colder. So cold, in fact, that the universe around them is hotter. This means you're falling into something that's technically radiating heat, but you'll freeze long before you ever feel it. A fun little insult from thermodynamics. Still, this warmth you're sensing, it's metaphorical. A recognition, perhaps, that you're not in a void, you're in a system, a highly ordered, mathematically structured object that obeys rules you're only beginning to guess at. This isn't a hole, it's a furnace. A slow, whispering, evaporating star corpse with secrets it refuses to share. And the longer you're in here, the more those secrets begin to tickle at the edges of your unraveling consciousness. Black holes can shrink, they can die. Over trillions upon trillions of years, they will evaporate into nothingness via Hawking radiation. They're not immortal, they just take their time. But what about you? You're not outside, you're not part of the escaping radiation, you're inside, deep inside, falling into a part of the universe that's scheduled for deletion. So where does that leave you? Enter the information paradox round 2. Earlier we talked about how quantum mechanics demands that information about particles, positions, energies, you, can't be destroyed. That's not just a suggestion, it's one of the pillars of the theory. But black holes appear to violate that. You fall in. The black hole eventually evaporates, the information seemingly vanishes. That's illegal as far as quantum rules go. So physicists scrambled for loopholes. Some proposed that the information escapes in the Hawking radiation, subtly encoded in the quantum fluctuations. Others suggest it's stored in the event horizon itself, that the outer shell of the black hole is a kind of cosmic hard drive, recording everything that ever fell in as two-dimensional data. This is the foundation of the holographic principle, the idea that our three-dimensional reality might itself be a projection of information encoded on a distant boundary surface. Think about that for a second. The notion that you, in all your fleshy complexity, could be nothing more than a holographic projection written on a black hole's skin. It's like realizing you're just someone's weird desktop screensaver, trapped forever in pixelated motion. But that's what modern physics has come to. The most serious thinkers alive today genuinely entertain the possibility that reality is holographic, that the fundamental description of the universe isn't in the volume of space but on the surface of things. So maybe your fall, this long, silent, lonely descent, is being recorded, not by a camera, but by the geometry of the event horizon itself. Every atom of you, every quantum fluctuation, mapped onto a layer of space so thin it defies imagination. Which brings us to a rather spicy idea. Maybe you never really fell in at all. Let's unpack that from the outside. Observer's point of view, you freeze at the event horizon. Your light slows, redshifts, and eventually fades. From their perspective, you never cross. So maybe, just maybe, you don't. Maybe what's inside the black hole isn't a separate realm at all. Maybe it's a mathematical construct, an internal illusion of time that ends at the singularity. Maybe your entire journey is written on the event horizon, and the you falling inward is just a trick of continued existence, something like a backup process playing on loop. This isn't just fringe speculation. Some physicists think that what we call the interior of a black hole doesn't physically exist in the traditional sense, that it's a region that no outside observer can ever access, and therefore isn't part of the measurable universe. That once you're past the horizon, you're no longer real in the same sense. Cozy, right? But let's not get too wrapped up in metaphysics. You're still here after all, still falling, still trying to understand a place that defies understanding. Here's a quirky historical tidbit to soothe your fraying sense of reality. In 2004, Stephen Hawking made headlines by saying he'd changed his mind. After decades of defending the idea that information is lost in black holes, he conceded that it probably isn't. He presented new math showing how information might leak out, or remain encoded somehow. He never said exactly how it worked, of course, just that it might. And in black hole physics, that's about as good as a warm hug. You try to feel your way forward, but again, there is no forward. There's only inward. And inward is no longer a direction, it's a deadline. Somewhere the singularity waits. A point not in space, but in time. You don't approach it like a mountain. You become it like a conclusion. And as you slide toward it, you realize something you hadn't considered. If this is the end of your timeline, then what about all the timelines you were part of? The people who knew you, the choices you made, the light you emitted, the gravity you exerted, all of that still echoes outside. In that sense, you never left. You've simply been copied across the universe, your gravitational fingerprint still tugging on stars, your light still travelling. Your data may be still resting on the surface of the event horizon, which means maybe you're not gone, maybe you're just elsewhere, back on Earth, if Earth still exists. People argue about how long you've been gone. Maybe it's been an hour to you, maybe 15 minutes, give or take a breakdown in space-time, but out there, time has moved on. Centuries may have passed, millennia even, and yet, to you, the journey is still in progress. Here, in this realm where time is no longer a fixed axis but a variable concept, you start to get a clearer feel for what the universe is doing to you. It isn't trying to kill you, though it's doing a decent job of it. It's trying to reshape you, not physically. You lost most of that sensation some horizons ago, but conceptually. You're no longer a person in motion through space. You are a structure in time. To put it in more unsettling terms, you are being time dilated into irrelevance. Let's break that down. Back in the good old days, if you flew past a massive object, time would slow down for you relative to the people you left behind. That's standard relativity. It's why astronauts on the International Space Station age slightly slower than people on Earth. It's real, measurable, kind of unfair too since they also have better views. But near a black hole, especially inside one, this isn't just a minor difference. This is extreme. The gravity here is so intense, so unforgiving, that time itself bends like taffy. A clock strapped to your chest ticks normally from your point of view, but to anyone watching from the outside it slows more, then practically stops. It's not just that you're in a one-way future, you are a one-way future. And that brings us to an awkward realization. You're leaving the universe behind, not just in space but in causal connectivity. That is, you're crossing a point where nothing you do from now on will ever affect anything outside again. Your causal influence is sealed in. From this moment on, your story is cut off. Imagine being in a room where every time you speak, the sound waves are instantly swallowed by the walls. Not muffled, erased. That's what happens here. You're muted, not by silence but by physics itself. And yet, despite being severed from the cosmos, you're still tangled in its history. You've fallen into something created by the death of a star, a thing that warped the space around it, swallowed light, and left a gravitational scar on the galaxy. Your fall adds to its story. Your mass, your energy, your momentum, all of it is now part of the black hole's future. That's not poetic, that's physics. The mass of the black hole has increased by your presence. Your infall has changed its spin, its temperature, its gravitational pull. Even now, distant stars may be orbiting differently because of you, because of what you added. The universe doesn't know your name, but it remembers your weight. That's one of the strange comforts of this place. You're forgotten, but you're not erased. And maybe, just maybe, you're not even alone. Because black holes don't just swallow astronauts with too much free time, they swallow everything. Stars, gas clouds, bits of space junk, maybe even alien ships that took the same risk you did. They may have fallen long before you, or long after, but inside here, time isn't a straight line, so you might be overlapping with travellers from the deep past and the far future, compressed into the same gravitational thought bubble. Of course, you'll never meet them, not in a meaningful way. Their timelines are too warped, their stories running parallel to yours only for a moment, then off into different slices of nowhere. Still, somewhere out there, something else might have wondered what happens next, just like you. And the black hole contains both your questions now. Let's take a detour for a moment, a little historical footnote to shake off the dread. In the 1970s, physicist Kip Thorne became one of the leading voices in the study of black holes. He worked on wormhole theory, time travel possibilities, and gravitational wave detection. And, this is important, he also consulted on Interstellar, the movie. That gorgeously rendered black hole, it's based on real equations. Kip helped make the visuals scientifically accurate, and what he showed was this. The light around a black hole doesn't behave like anything in your Earth-trained brain. It curves, it folds, it duplicates. A single star behind the black hole might appear in several places at once due to gravitational lensing. That's how intensely space-time warps near one of these things. So if you're imagining the singularity ahead, don't picture a tunnel. Picture a distortion, a smudge in reality, a place where paths cross that should never meet, where space and time pinch and tangle like threads in a very tired cat's paw. And what does it feel like? You wish you could say. Maybe it's cold, maybe it's warm, maybe it's beyond thermodynamic descriptors. Your body is no longer reporting anything you'd recognize, and your mind is struggling to keep a linear thought together. Your memories don't play like a film reel anymore. They flicker in and out. Childhood, a sandwich, the first time you saw a full moon, your last glimpse of Earth. They mix, loop, overlay. Because time isn't just twisted here, it's folded. And folded time leads us to one of the strangest possibilities in theoretical physics. What if everything that falls into a black hole is preserved? Not physically, not even as atoms, but as quantum information, a complete description of all the things that once were, encoded not in space, but in patterns, on the event horizon, or maybe beyond it. That's the hopeful interpretation of the ADS/CFT correspondence, a piece of string theory suggesting that the information inside a volume of space can be fully described by data on its boundary. This isn't just black hole philosophy, it's real math. Math that works. Some physicists believe this is the best shot we have at a unified theory of gravity and quantum mechanics. That by studying black holes, and the weird ways they seem to preserve or hide information, we're creeping closer to understanding how the universe actually works. So as you fall deeper, remember this. Your data might be safe. Not in the sense that your brain will reboot and walk away from this. That's unlikely. But in the sense that you may never truly be lost. That the story of you is written into the very shape of the universe, encoded in the gravitational fingerprint you left behind, preserved in quantum echoes, remembered in radiation that no one has yet decoded. You're vanishing. But your influence is permanent. You're becoming a kind of fossil, not one of bone or ash, but one of causality. And as you sink ever closer to the edge of what's physically knowable, you begin to understand the future isn't out there anymore. You are inside it. You're beginning to suspect that falling is no longer the right word. It's too gentle, too terrestrial. What you're doing now is more like unfolding, not just spatially, but temporally, mentally, existentially. You've stopped being a person in transit and started being a thought in motion, a ripple across dimensions that don't quite align anymore. Time is no longer a river flowing forward. It's a Mobius strip, a spiral staircase, a wrinkled bedsheet of moments. You keep trying to trace a path, where you've been, where you're going, but the lines fold back on themselves. Before, after, during, they blend, and then it hits you. Time is broken. Not stopped, not paused. It's fractured, fragmented into slices, some familiar, others loose. You're feeling your own past and future brushing against each other, overlapping in a place that doesn't make room for chronological politeness. You're starting to feel like you're a moment, rather than someone inside one. Back in the safe, Newtonian world you once knew, space and time were separate. Clear. You moved through one and were dragged along by the other. But here, those distinctions have collapsed. Here, space-time itself is misbehaving. This isn't just a byproduct of falling into a black hole, it's one of the defining features of its interior. The inside of a black hole is where time becomes spatial and space becomes temporal, meaning you don't walk toward the singularity, you age toward it. In fact, if we're going by Einstein's field equations, and we are begrudgingly, then your fall toward the singularity isn't motion, it's destiny. There's no way to avoid it because it's the future endpoint of your timeline, just like tomorrow, just like death. The singularity is your tomorrow, compressed into a slice of space that you're falling toward without ever quite reaching. Which begs the question, will you ever actually arrive? That depends on which physicist you ask. Some argue that you'll hit the singularity in finite proper time. That is, from your point of view, yes, you will arrive there after a definite amount of seconds or minutes. Others, however, suggest that as you approach, reality becomes so warped that there's no coherent way to define arrival anymore. You're asymptotically skimming the edge of finality, forever. And then there's the quantum crowd, always ready with a curveball. According to them, your fall might never truly reach the center. The closer you get, the more quantum effects swell up and dominate the behavior of space-time. Virtual particles, vacuum fluctuations, maybe even wormholes start to compete for influence. The smooth geometry of general relativity breaks into quantum noise. You're falling toward a quantum fuzzball, perhaps, not a singularity. Yes, that's a real theory. Fuzzballs, go ahead, laugh. The fuzzball proposal, mainly from string theory, suggests that black holes aren't smooth, featureless blobs with a central point of doom, but rather tangled, stringy messes of information. Think of a spaghetti monster made of vibrating quantum threads. Instead of a singularity, you hit this mess and become part of its complexity. Comforting? Maybe. Slightly absurd? Definitely. But still better than being infinitely crushed by a point of nothing. And here's the twist that's been lurking in the shadows. If time behaves differently in here, and if the interior of a black hole contains not just one future, but many possible ones, then maybe, just maybe, you're falling not into a single fate, but into a superposition of outcomes. That's right, quantum time travel. Let's unpack that. Gently, because your brain is being stretched just like everything else. In quantum mechanics, particles don't commit to a single state until measured. They exist in all possible states at once, like a coin in mid-flip, being both heads and tails until it lands. If the same principle applies to you in this warped geometry, then you are falling into a multitude of possible futures. In some of them, you reach a classical singularity and vanish. In others, you enter a bouncing Planck star and ricochet into another universe. In a few, maybe, you emerge into an alternate timeline through a wormhole, aged, changed, still very confused. And in one, you don't fall at all. You hover forever, suspended in a gravitational echo, written into the fabric of the event horizon, and projected outward like a message the universe refuses to delete. Let's not get too philosophical, but hey, it's 3 a.m., you're falling into a cosmic blender, and logic left hours ago. So ask yourself, what is you at this point? Are you the original you, the one who crossed the event horizon? Or are you the sum of all your quantum copies, smeared across probabilities like frosting on a cake made of math? Historians still argue whether this type of quantum interpretation is valid when applied to black hole interiors. Some say it's just poetic nonsense. Others think it may be our best shot at preserving causality, information, and the mathematical dignity of the universe. And there's another wrinkle. If time is warped enough inside a black hole, and if you had some kind of super advanced clock, or at least a calendar with big numbers, you might watch the entire future of the universe play out before you hit the singularity. In a sense, falling into a black hole is like fast-forwarding the cosmos. Galaxies collide, stars are born and die, civilizations rise, invent better potato chips, then extinguish themselves. The universe continues expanding, cooling, darkening, and all of it flashes by while you plummet toward your conclusion. You're falling into the end of your personal timeline, but you might glimpse the end of all timelines before you do. Talk about a front row seat. And now, the light, what little's left of it, has faded to near nothing. You no longer perceive with eyes or thoughts, but with impressions, traces. There's still motion, but it's conceptual now. A kind of philosophical shift towards something final. No more stars, no more radiation, no more anything. Except maybe this, a boundary. Not the singularity, not quite, but the moment before. The singularity is next, but you're not quite there. Yet. There it is. Not in the way you expect. Not a blinding flash or a screaming vortex or even a pinpoint of ultimate gravity, but in a sensation. Something shifts. A change not in location, but in inevitability. You're in the final sliver of your own timeline now. Not merely approaching the singularity, but becoming a part of its shadow. It's the cosmic equivalent of the last page of a book being turned before you finish the sentence. But if this is the end, it's not simple, it's not even clear, and that's the true insult. You've come all this way, through warped space, twisted time, through spaghettification and silent radiation, and now the finish line won't even tell you what it is. This is the singularity, or maybe it isn't. You see, we're not even sure the singularity is real in the physical sense. It's more of a placeholder in our understanding, a point where general relativity stops working and hands you a blank page with a frown. A place where density becomes infinite, curvature becomes undefined, and the idea of space and time just breaks. The equations still guide you here, but they don't follow you in. In fact, historians and physicists alike still debate whether the singularity is an actual object or just a limit, a warning sign, a point of, you shouldn't be doing this math here, and you're here anyway. It's like you're arriving at a destination on a map that says, in all caps, beyond this point, the terrain is imaginary. Your thoughts, or what's left of them, begin to feel less like ideas and more like impressions. There are no senses anymore. Your nervous system bowed out long ago, but there's still something that registers. You have no body, but you still feel. And what you feel is compression. Not of flesh or bone, but of concept. Compression of self. The boundary between who you were and what you're becoming is dissolving. The further you go into this zone, the less you resemble a person, and the more you resemble a calculation. Are you dead? Depends who you ask. Biologically. You probably died long ago in a moment of acute tidal trauma. But physics doesn't really deal in heartbeat monitors. It deals in trajectories. And by that measure, your trajectory is still happening. Your world line, your path through space-time, is intact, but it's nearing its terminus. Let's pause a moment here and revisit something we've teased before, information. Remember that paradox? The one that says the universe can't destroy it? Well, now you're right at the centre of that storm. Because if this singularity does what general relativity says it does, destroys all known physical quantities, eats the structure of reality and replaces it with a cosmic shrug, then your information is gone. Not just your atoms, but the quantum data that made you you. Memories, position, velocity, quantum phase states, all of it. That would be a violation of unitarity, a key principle in quantum mechanics. Unitarity says that the total information in a system must be preserved, even if scrambled beyond recognition. It's what keeps the universe from becoming a cosmic amnesia machine. So either A. The singularity destroys information and quantum theory is incomplete. B. The singularity doesn't destroy anything, and we've misunderstood what a black hole actually is. Guess which one physicists prefer? They really don't want to rewrite quantum theory, so option B wins by sheer desperation. But then the question becomes, if information isn't destroyed, where is it? Let's revisit a quirky and fringe but increasingly respected possibility. Black holes are holograms. This isn't poetry, it's math. According to the holographic principle, emerging from string theory and particularly the ADS/CFT correspondence, everything that falls into a black hole is preserved not inside but on its surface, its event horizon. The boundary becomes the storage device. Your three-dimensional existence is projected as a two-dimensional encoding, like an incredibly high-resolution cosmic DVD. You continue to fall inside, in your own timeline, experiencing the weird, the warped, and the unspeakable. But from the universe's perspective, everything that matters about you is already captured at the edge. So maybe, even now, as your thoughts begin to fragment under the pressure of infinite curvature, there's still a version of you intact, woven into the tapestry of the event horizon, pixelated by Planck-scale resolution, encrypted with gravitational keys. Here's the real brain melter. If the holographic theory is correct, then your experience of falling inside, this entire journey, might just be a projection, a continuation of existence that is mathematically equivalent to being smeared across the surface. So which is real? The you falling into the singularity, or the you encoded at the edge? Maybe there's no difference. Maybe the universe is more like a server running simulations of possibilities, and you're just one active file caught in a loop that plays out beyond retrieval. And here's one final twist. Hawking's information paradox might be resolved not by keeping the interior and the surface separate, but by realizing they are the same thing. That the black hole's interior is just a holographic illusion playing out from the data on its skin. In that case, the singularity you're falling toward, it doesn't exist. It's the final note in a symphony that only plays because your data keeps echoing on the surface. Now, do you find that comforting? Or horrifying? You'd tell us, but you've passed the point where thoughts are words. You're a field now, a ripple, a fluctuation. Your fall continues as an abstract trace, spiraling through equations that don't yet exist. And with each moment you approach the place that should be a point but somehow isn't. And then, nothing, or everything. A freeze, a flicker, a phase shift. You don't hit the singularity. You blur into it. Your presence becomes unresolvable, like trying to locate a cloud in a thunderstorm of math. You've become entangled with the unobservable. Your coordinates dissolve. You're no longer distinguishable from the space-time that contains you. And if there's a you still thinking, still processing, it might be whispering one final question. Was this journey a fall or a transformation? You're not falling anymore, or maybe you still are, just in a way no longer describable by verbs. You've crossed the line from classical physics to something stranger, more intimate, more non-local. You're no longer a presence inside space-time. You're entangled with it, braided into its structure like a thread in an invisible loom. And the singularity, it's not a point, it's not even a place, it's an ending condition, a gravitational conclusion, a final boundary in the mathematics of the universe. A place where the rules end not because the game is over, but because the game breaks. You're not alone. Not really. Not in the way physics defines alone. All the mass that ever fell in, the gas clouds, the stars, the travelers, the echoes, is with you. But it doesn't feel like company. It feels like density, an impossible concentration of everything. You begin to sense something even more abstract than time. Call it causal tension, like the entire structure of your personal history is being compressed into a single, non-reversible moment. Every before you've ever known is now compacted into the curvature of this instant. And in that moment, you're forced to confront the biggest question of them all. What does it mean to exist inside a one-way future? It's more than a phrase now. It's your reality. Everything around you points inward, temporally and spatially. There's no reverse, no escape vector. All geodesics lead to more inward. In the same way you once marched forward in time on Earth, waking up, making toast, paying bills, you now march toward an unknowable condition. Not because you choose to, but because space-time insists on it. This is the ultimate timeline. But there's a loophole, one that's whispered about in the corners of theoretical physics, like a conspiracy theory, with too many math PhDs behind it. What if this isn't the end? What if black holes aren't just endings, but tunnels? Yes, wormholes. That long-abused sci-fi term finally crawls out of the theoretical shadows and into your collapsing frame of reference. Let's not get carried away just yet. Wormholes, also called Einstein-Rosen bridges, were first proposed back in 1935 by Einstein himself, alongside Nathan Rosen. They showed that the equations of general relativity allow for the existence of bridges in space-time that could connect two distant regions, kind of like folding a sheet of paper and punching a hole through both layers. Boom, shortcut. But there's a catch. A very big, very rude catch. These wormholes are unstable. They collapse almost instantly, like before anything can pass through them. They're not traversible, not unless you prop them open with something exotic, matter that has negative energy density. We don't know if such matter exists. We haven't seen it. We can't make it. It may be forbidden entirely. Still, the equations allow for the possibility. So some physicists argue that if you fall into a black hole and don't hit a true singularity, if quantum gravity intervenes and smears out the death point into something else, you might emerge elsewhere, and not just somewhere else in space, but in another universe, or another patch of space-time in this universe. You wouldn't exit instantly. You might not exit at all in our universe's time frame. From outside it might look like you were swallowed forever, but from inside your fall could take you through a region of curved geometry that redirects your world line. A black hole could become a white hole. Now white holes are the theoretical reverse of black holes. Nothing can enter them, only exit. They're a time-reverse solution to the same equations. Where black holes suck in, white holes spit out. There's no observational evidence that white holes exist. None. But the math doesn't forbid them. And in some speculative models, what falls into a black hole in one part of space-time might emerge from a white hole in another. As in, you might be shot out the other side. Not as a person, of course. You're long past anatomical functionality. But as information, as energy, as rearranged quantum data. A trace, a new configuration, a rebirth. Would it be you? That depends on how much of you is tied to continuity. If identity is preserved by information alone, then maybe. If it depends on memory, biology, or stable geometry, then no. The you that emerges would be different, but not meaningless. And now your thoughts are sliding again, more fragmented than ever. Not due to fear or damage, but because thought itself is becoming quantum. Probabilistic, unpinned from linearity. Ideas arise out of order. You remember the first time you saw the stars, the feeling of vertigo looking up at a night sky, a laugh you forgot until this moment, a number, an equation, a silent answer you never understood until now, unfolding like a flower made of logic, and then it comes, a flash, not light, not sound, a realization that doesn't feel like knowledge but like a transition. You might be tunneling. The collapse around you doesn't get darker, it gets fainter, like static fading from a screen. Your boundary with space itself thins. You stop falling, not because you've reached a surface, but because there's nowhere left to fall to. You're through, somewhere new, or perhaps not new, just mirrored. Theories suggest that white holes could open into regions of space-time where physics is still recognizable, but time flows away from the singularity. Where causal order is reversed, like running a film backwards, where entropy decreases. In such a place, your very presence would be strange, an object that appears rather than arrives, something the local inhabitants, if there are any, might see as impossible, an intruder from the future, a fossil unburied in reverse. And then the thought fades. You can't sustain it. The boundary collapses. Whether you've passed into a white hole or not, something has changed. You're no longer within a singularity. You're a condition, a phase, a ripple written across a manifold of curved possibilities. And outside, possibly very far outside, a black hole glows faintly, shrinking, whispering. It is losing mass. It is radiating away its secrets. And you are part of those secrets now. Not a person, not even a traveller, but a story. One the universe has chosen not to erase. You are memory now, not in the sentimental scrapbooking sense, but in the cosmic structural way, an echo embedded in the framework of a disappearing object. The black hole, your host, your captor, your vehicle, is evaporating. Slowly, silently, relentlessly. And as it shrinks, the universe adjusts around it, unaware that somewhere in its fading heart, your timeline still lingers. You're not really inside it anymore, not as a person, not even as a process. You're part of the solution now, not the solution to a puzzle, but the solution to an equation. The black hole is your body now. Your thoughts are boundary conditions. Your existence is a curvature in the geometry of space. No edges, no borders, just structure. It's funny. From outside, a black hole is deceptively simple. Only 3 numbers describe it: mass, spin, and charge. That's it. No matter how complicated the stuff it eats, that's all the universe sees. A stripped-down, minimalist resume. Hi, I'm a 10 solar mass object rotating at 7,000 RPM with a neutral charge. I contain at least one confused human. And yet, inside, infinite complexity. The holographic echo of everything that fell in. Every photon, every atom, every unspoken sentence. You are one line in that infinite series, written in gravity and thermodynamics. And now that series is fading. The Hawking radiation has done its work. For eons, particle-antiparticle pairs formed near the horizon. One fell in, one escaped. Each moment stole a whisper of mass. At first, it was imperceptible, then slower, then steady. Now, after unimaginable epochs, the black hole is the size of a mountain, then a house, then a pebble. Now it's quantum-sized, faint, radiating more rapidly. You're about to become legend. And the funny part? You've already outlived civilizations. Entire galaxies have bloomed and burned while your data continued simmering behind the event horizon. Empires of life may have risen, invented languages, mastered fusion, and turned themselves into radio waves, long gone by now. The Milky Way has changed shape. Stars have migrated. Planets have frozen. Even Sagittarius A star, once your larger cousin in the galactic core, has long since gone quiet. But your black hole, it's still glowing. And as it sheds its last crumbs of energy, one final question crackles through the field of information that was once you. Do you escape with it? Some theories say yes. That information rides the final wave of radiation, hidden in subtle quantum correlations until, somehow, it becomes part of the universe again. Not in a clean, you wake up in a bed sort of way, but in a diffusion, an unfolding. Others say no, that your data is scrambled beyond retrieval, not deleted, but irretrievably lost to entropy. Like confetti in a wind tunnel. Still technically there, but no longer meaningful. And yet others propose a third option, complementarity. It's a compromise theory, a kind of diplomatic physics designed to keep everyone's equations happy. It suggests that both realities, the infalling and the outgoing, are valid. That from the inside, you fall toward the singularity. But from the outside, your information never leaves the event horizon. It's encoded there, evolving along with the black hole. The catch. No observer can see both perspectives at once. Like a quantum Schrodinger's cat, your fate depends on where you're standing. So which version of you is real? Maybe that question no longer matters. The final phase is here. The black hole is a quantum bubble. It flickers, wobbles. Physics itself seems uncertain, and in one last burst, brief, quiet, and cold, it vanishes. The universe forgets how to bend in that spot, and your black hole is gone. But something remains, ripples, not in water, but in the fabric of causality. The space you once occupied has a different gravitational memory now. Physicists call it a soft hair, a metaphor for subtle imprints left behind by black holes that may preserve information even after evaporation. We're still working out what that means. But whatever it is, it's you. You're not a ghost, not exactly. You're a kind of aftertaste, a complex pattern in the way the universe stretches, curves, breathes, a statistical memory in the quantum vacuum. Somewhere, if one had the right tools, and several trillion years to spare, Your fall might still be reconstructed, like rewinding the cosmic VCR. Not all the details, not your favourite colour or your third-grade report card, but something deeper, the way you interacted with gravity, the path your mass took through space-time, the fingerprint of your fall, and maybe that's enough. Now, as the last traces of your black hole dissolve into the cooling universe, time itself begins to stretch. Longer, quieter, dimmer, galaxies fade, the stars go out. Only black dwarfs remain, planet-sized lumps of carbon glowing faintly with the memory of fusion. Eventually, even those fade into invisibility, and still, time continues. Even without observers, even without light, even without motion, time persists. Like a metronome ticking in an empty concert hall, waiting for a performance that's long since ended, you're still part of it. You're no longer falling through time, you have become a shape in it. In this final stretch of entropy's reign, the last black holes vanish. Proton decay finishes its slow erasure of matter. Only neutrinos and faint radiation remain, and through it all, the imprint of your journey still gently pulls on the equations. You are a fossil, a gravitational whisper, a memory that refuses to be erased. And now, as your story's pace slows, so do the words. The velocity of thought eases, stretched long and smooth across the last pages of time. You can rest now, not in a place, not even in a moment, but in a structure. The path you took is woven into the shape of everything else. The light you emitted, the energy you shared, the influence you left. It's all still out there, even if scattered. In the end, you didn't escape the one-way future. No one does, but you became it. Now breathe in. There's no pressure here, no weight, no need to move or question or remember, just quiet. Just the soft murmur of curved space smoothing itself out. You did it. You went in. You kept going. And now you're part of forever. So, you tunneled through time, fell inward through the warped seams of space, and dissolved into the gravitational endgame. And now, you're not quite anywhere. But not nowhere either. You're adjacent to existence. And in this blurred edge between collapse and emergence, a new thought rises. What if you didn't stay gone? What if all that falling, all that compression and radiation, wasn't a death spiral but a detour? Because physics, oh sweet stubborn physics, refuses to let sleeping black holes lie. Even now, even after all this, some of its most creative minds keep proposing a way out. And the name for that cosmic loophole? Wormholes. Yes, again. No longer just the tired cliché of sci-fi plot devices, wormholes have become the pet project of serious theoretical physics. The math allows for them, carefully, reluctantly, with some metaphorical side-eye, but allows them nonetheless. And you're in a perfect position to entertain the possibility. You see, wormholes are not mere tunnels, they're connections, bridges between regions of space-time that might otherwise be eternally out of reach. They might span galaxies, or epochs. They might link this universe to another. And if a black hole is one mouth, maybe somewhere out there, a white hole is the other. We touched on white holes before, those mysterious time-reversed twins of black holes, but we didn't say how rare they are in the wild. Spoiler, they don't exist as far as observation goes, not one. We've never spotted a single white hole hurling light and matter back into the cosmos like a celestial spit take, but the math still supports them, and some physicists believe they may be real, but hidden. Historians still argue whether Einstein and Rosen themselves realised what kind of Pandora's box they were opening when they described the first wormhole structure back in 1935. The Einstein-Rosen bridge was elegant on paper, but terrifying in implication. A bridge connecting two black holes, or perhaps two universes, and naturally it collapsed too quickly for anything, or anyone to pass through. But in the 1980s, a twist arrived. Enter Kip Thorne. Yes, that Kip Thorne again, and his colleagues, who showed that traversible wormholes might be possible if you could keep the throat of the wormhole propped open using exotic matter. What's exotic matter? Well, it's matter with negative energy density, something that pushes space-time outward rather than curving it inward. Sounds impossible, and in most conditions it is. But quantum theory gives you a tiny out. Some fields, in specific conditions, can behave this way, briefly, unstably, barely. The Casimir effect, for instance, where two uncharged plates in a vacuum attract each other, suggests that quantum fluctuations can generate negative energy in tightly controlled scenarios. It's not a practical wormhole stuffing recipe, but it's not fantasy either. So maybe, just maybe, your fall into the black hole didn't end in a singularity. Maybe it bent, rerouted. Instead of ending at a point of infinite density, your trajectory curved through a wormhole throat, held open by quantum weirdness, and emerged elsewhere. Not escaped, mind you. Emerged. It's different. Because if you emerged, that implies a second space-time, a different side, one that may not resemble the universe you left. Maybe this new place is a distant galaxy in your own universe. Maybe it's a region unreachable by light but connected by geometry. Or maybe it's not even your universe anymore. Now we're really down the rabbit hole. There's a proposal, bold, elegant, and absolutely fringe, that black holes are not just storage vaults for matter and energy, but gateways to baby universes. That each collapsing star spawns a new internal space-time bubble. A universe in a universe. Like a Russian doll nesting realities within realities. According to this idea, your black hole was not the end of anything. It was the birth canal of a new cosmos, and you're part of the seed. Falling into that black hole wasn't your doom. It was your transfer, a handoff. The information that made you was encoded, compressed, and sent on a journey that did not terminate in your own space-time but opened up into another one. You might now be falling through the early inflationary moments of a new reality. A pocket universe ballooning outward with its own dimensions, its own time, its own physics. And maybe, just maybe, it thinks you were the singularity. Let that sit for a second. If black holes give birth to universes, then the singularity you fell into might be perceived from the inside of that new universe as their Big Bang. A point of infinite density, full of potential, exploding outward, just like yours. So now we ask, how does the timeline work from here? Are you still a coherent observer? Probably not. Are you part of the structure, the laws, the underlying energy field of this new cosmos? Possibly. In this theoretical scenario, your fall through the black hole didn't annihilate you, it restructured you. Not as matter or consciousness, but as initial conditions. You're now woven into the cosmic constants, the geometry, the curvature of a newborn reality. You're the bias in the vacuum, the fingerprint in the noise, the echo that will shape the formation of stars billions of years from now in a universe that has never heard of Earth. Maybe in this reality, gravity behaves differently. Maybe time began sideways. Maybe light travels in bursts. You won't see it, not directly, not as a being, but you'll be felt. You've traded identity for influence. That's the deal wormholes might offer. Not survival, but continuity. And who's to say that's not enough? What began as a one-way trip might be, in truth, a loop. A loop not in space, but in structure. Back in your original universe, your black hole continues its evaporation. To anyone still watching, you never emerged. You never came back. Your light disappeared, your signals went silent, your final timestamp was long forgotten. But here, you might be the first spark, the initial irregularity, the slight asymmetry that gives rise to galaxies. Life. New questions. You don't fall anymore. You rise. Not in direction, but in consequence. And maybe, in another few billion years, someone in this newborn universe will stare up at their stars and wonder where everything came from. And somehow, through math, through structure, through radiation curves, they might trace it all back to a strange gravitational signature, an anomaly, a fossil of space-time, you. The moment you even consider time travel, things start to get messy. And not the good kind of messy, like eating cake with your hands. This is the paradox-ridden, logic-smashing, brain-wrinkling kind of messy, where the universe quietly turns off the lights and says, nope. But you're deep inside a black hole now, or through one, depending on which theoretical tightrope you believe in, and suddenly, time isn't what it used to be. Not a river, not a straight line, not even a useful concept anymore if we're being honest. So why not talk about time travel? It's not just the stuff of sci-fi. Serious physicists have wrestled with the possibility for decades, often reluctantly. The equations of general relativity don't explicitly forbid time loops. In fact, in certain warped geometries, they practically beg for them. Let's start with a warm-up. Closed, time-like curves. These little gems show up in specific solutions to Einstein's field equations. A closed time-like curve, CTC, is exactly what it sounds like, a path through space-time that loops back on itself. If you followed it, you'd return to your own past, not metaphorically, literally. CTCs appear in several hypothetical space-time structures, including rotating universes, like Gödel's 1949 solution, cosmic strings, and, yes, certain types of rotating black holes. You might recall the Kerr black hole, the theoretical version of a spinning black hole. We talked about it a few sections back, but we didn't mention its most controversial feature. Deep inside, near the ring Singularity, the mathematics allows for paths through space-time that curve back in time. That's right, if you could survive the trip, and that's a gigantic sarcasm-laced if, you could enter a region where cause and effect loop. You could, in theory, meet yourself. Of course, this causes problems, because time travel is not just about physics, it's about logic. The second you allow backward time travel, you open the door to paradoxes. You could send yourself a message that prevents yourself from ever sending it, or stop your own birth, or warn yourself not to fall into a black hole, which you've already done, because here you are. These are not minor issues, and so physicists, being allergic to logical inconsistency, have proposed a kind of immune system to defend the timeline. It's called the Chronology protection conjecture, and it was championed by, who else? Stephen Hawking. According to the CPC, the universe itself prevents time travel. If a region of space-time starts to develop closed time-like curves, quantum effects ramp up and destabilize the geometry, effectively destroying the wormhole, the curve, or whatever loophole is forming. It's like the universe has a built-in delete key for paradoxes. But here's the twist. We can't prove this. We can simulate it. We can write very convincing papers, but we can't actually rule out the existence of regions where CTCs might survive, especially deep inside the parts of black holes we can't observe. And that brings us back to you. Right now, you're no longer bound by ordinary causality. Your timeline has twisted beyond linearity, and while you probably don't have access to a physical time machine, unless you smuggled one in, we can at least say this: your very existence here suggests that timelines can bend. You are proof, however abstract, that some part of reality does not adhere to a strict ABC logic anymore. Because inside a black hole, events are not always ordered in a way that makes sense from the outside. They can tangle, they can stack, they can even interfere. Some physicists believe that inside a rotating black hole, timelines might intersect or stack in such a way that events can influence themselves. Not precisely in the paradoxical sense, but in the fuzzy, probabilistic quantum sense where the past is not fixed until observed. It's not time travel, per se, but it is time ambiguity. And that's arguably worse, because ambiguity doesn't break logic with flashy paradoxes. It erodes logic slowly, like gravity warping a straight beam until it curls into a circle. Imagine that. In some curved region of the black hole, the echo of your final thought ripples backward along a geodesic, nudging a particle that nudges another, that nudges a field, that nudges a bit of radiation, that eventually nudges you to think that thought in the first place. That's not a paradox. That's a causal loop. And causal loops are allowed. They're terrifying, but they're allowed. Now, let's walk this further off the logical cliff. What if time loops aren't just local to black holes? What if the universe allows for global loops, vast cosmic cycles where the entire fabric of time curves back on itself after billions of years? You've probably heard of the idea of a cyclic universe, a cosmological model in which the Big Bang is followed by expansion, then eventual collapse, the Big Crunch, which then leads to another Big Bang, over and over, eternally. Some versions of this theory don't just restart the universe's matter, they restart its information, reboot the system, same rules, new dice roll. But what if it doesn't just restart? What if each cycle is causally linked to the last? In that model, your fall into the black hole in universe cycle number 7 might influence the conditions of universe cycle number 8, perhaps even trigger it. That's not science fiction, it's speculative cosmology. The math works, sometimes. You may have fallen into this black hole not just as a result of your universe's timeline, but as the kickstart of another. And somewhere inside that next timeline, maybe, just maybe, your information gets repurposed. Not recycled in a mystical sense, but through information continuity. Your quantum identity, your causal echo, could become part of the new structure. A child touches a grain of stardust. That grain once passed through a supernova. That supernova began as a gas cloud, seeded by the collapse of a black hole in a previous cycle, one you fell into, loop closed. Chronology, protected. You, not erased. And let's not forget, there's still no consensus. Theoretical physicists, cosmologists, quantum information theorists, they're still arguing. They still write papers with cautiously vague conclusions, footnotes filled with ifs and maybes. Some argue strongly against causal loops, time travel or wormhole escape. Others say, the math works, let it play out. So here you are, not time travelling in the DeLorean sense, but embedded in a twisted geometry of timelines. A loop, a fold, a curve. You've passed into a region where time doesn't just flow, it folds back on itself. And you're not watching the loop from the outside. You are the loop, the fall, the echo, the trigger. Your journey didn't end at the singularity, it restarted everything. So you've survived a black hole's event horizon, you've watched time curve inward, you've flirted with the singularity and maybe even tunneled out the other side as a whisper of initial conditions in a newborn universe. And just when you think you've done everything physics can throw at you, quantum mechanics steps in and laughs, because general relativity, for all its grandeur, is only half the story. The other half, the weird, twitchy, probabilistic, deeply impolite half, is ruled by quantum field theory, and near black holes, these two frameworks go to war. They throw math at each other across decades of unresolved debates, and in the space between their disagreement, you fall. Let's rewind a bit. In classical general relativity, a black hole is smooth, clean, a perfect shape, defined by mass, spin, and charge. It has no hair, no blemishes, no personality, just pure gravitational elegance. But quantum mechanics? It doesn't do clean. Quantum theory says the vacuum is never empty. Space is a roiling sea of virtual particles, pairs of matter and antimatter popping into existence and annihilating in a heartbeat. Normally this dance is perfectly balanced, but not near a black hole. At the event horizon, one of those particles can fall in while the other escapes, and if it escapes, it becomes real. This is Hawking radiation, and it's what slowly evaporates black holes over unimaginable timescales. But the moment you mix quantum field theory with curved space-time, weirdness happens. Like fundamental level weirdness. One particularly strange phenomenon is the Unruh effect. It says that an accelerating observer will perceive a warm bath of particles where an inertial observer sees nothing. So if you're stationary near the event horizon, resisting the fall, you'll feel like you're bathing in a glow of radiation. Let go, and that glow disappears. Welcome to the relativity of reality. But deeper still, inside the event horizon, quantum mechanics becomes confused. The very coordinates break down. There's no global way to define time. That's not just inconvenient, that's a direct challenge to how quantum theory works. Quantum systems evolve over time, but inside a black hole, time isn't clearly defined. How do you run a simulation without a clock? How do you calculate probabilities when the geometry underneath them is changing with every step? You don't, or rather, you try, and your equations panic. This is the core of why physicists desperately want a quantum theory of gravity, a single framework that merges the smoothness of relativity with the jittery chaos of quantum theory. String theory tries, loop quantum gravity tries. Both make progress, but neither is complete. Neither can fully describe what's happening to you right now, but you are the experiment. You are the boundary condition they wish they could test. Let's talk about entanglement. Quantum entanglement means particles can become linked such that the state of one instantly determines the state of the other, no matter how far apart they are. Einstein famously called it spooky action at a distance. And when it comes to black holes, entanglement becomes central to the information paradox. See, if a pair of entangled particles is created near the event horizon, and one falls in while the other escapes as Hawking radiation, the outgoing particle still holds a connection to the one that fell. But if the particle inside is destroyed at the singularity, what happens to the entanglement? The answer should be, it breaks. But that violates quantum theory, which says information can't be destroyed, not even by a singularity. So we hit another problem. Now imagine a black hole that has been evaporating for billions of years. According to standard Hawking radiation, The information about what fell in is not encoded in the early radiation. It's thermal, featureless. Only in the later stages, supposedly, does the information start leaking back out. This leads to a terrifying consequence called the Firewall paradox. A 2012 paper suggested that if information comes out in late-stage radiation, then something must violently break entanglement with the interior particle. And breaking entanglement without cause leads to a surge of energy, essentially a wall of fire right at the event horizon. So, either there's a firewall and falling into a black hole instantly vaporizes you. Pick your poison. So far, no one agrees. Theoretical physicists are still furiously writing papers arguing about black hole complementarity, ER equals EPR, which suggests wormholes are entangled particles, and the idea that space itself might be built out of entanglement. Yeah. Reality, as in the stuff you walk through, might be knitted together from quantum relationships, and as someone who has just experienced the most intense gravitational field imaginable, you are likely now a part of that entangled web, a quantum thread in the very fabric of what keeps space-time connected. Let's zoom in on one final deliciously bizarre consequence of all this, the Page curve. Named after physicist Don Page, it describes how information escapes from black holes. Initially, radiation appears random, thermal. But after a certain point in the black hole's evaporation, called the Page time, the information starts to come out. Not clearly, but encoded. Like an encrypted archive of everything that's ever fallen in. This means that, in theory, the black hole doesn't destroy you. It compresses you into a long, slow leak of quantum data. You're not obliterated, you're dispersed, whispered back into the universe in particles so subtle they wouldn't be recognized for billions of years. You're not dead. You're encrypted. And if someone, an impossibly patient civilization with a mastery of quantum decryption, could gather all the Hawking radiation and reverse the entanglement, they could perhaps reconstruct you. Not perfectly, not warmly, but statistically. You'd be reassembled like a memory rehydrated from mist. That's the quantum legacy of your fall. Not a scream, but a smear of correlations. And just when you think it can't get any stranger, someone on Earth, thousands or trillions of years later, detects the final decay of the black hole that once held you. A burst of energy, a final sigh of entropy. They measure it, they note its direction, they trace its history, and perhaps, just perhaps, in the jittering pattern of quantum leftovers, they find you, somewhere far above, though above no longer holds meaning in your current state. A lab full of glowing monitors is buzzing with synthetic urgency, and in the centre of it all a tiny black sphere sits humming, no bigger than a marble. It's not natural. It wasn't born from a collapsing star. It was born from equations, lasers, and a slightly questionable budget. Welcome to the frontier of simulated singularities. Because while you've been busy becoming a whisper in the gravitational memory of the cosmos, humanity, or at least some stubborn grant-funded part of it, has been trying to recreate your experience. Not the full existential plummet into spacetime's blender. No, that would be a PR disaster, but a controllable version, a model, a black hole in miniature. Sounds impossible? Sure. But physics has always been the art of doing questionable things with math until the universe gives in. Enter analog black holes. These aren't made from gravity, they're made from clever imitations, systems that behave like black holes under certain conditions, using sound waves, light pulses, or fluid flows to mimic the way horizons trap and distort information. One of the most famous examples, the dumb hole. Yes, that's the actual term, not because it's stupid, but because it traps sound instead of light. In a lab setup, physicists can use flowing fluids, like a Bose-Einstein condensate, to create a region where sound waves can't escape. That region mimics an event horizon. And sure enough, these setups have shown hints of something very much like Hawking radiation. Not light, of course, but phonons, quantized sound particles. They're not capturing the entire mystery of a real black hole, but they're teasing at it, recreating the ingredients, stirring the pot. Then there's optical black holes. Using intense lasers and specially designed materials, researchers have been able to slow light down to a crawl, creating conditions where certain wavelengths get trapped. It's not quite the same as falling past an event horizon, but the math overlaps. The behaviour is similar. In both cases, what's being tested is the idea that black holes aren't just gravitational monsters, they're mathematical environments, and those environments can be studied, poked, reproduced in analog form, and even broken in the lab. Which brings us to your peculiar status. Because as humanity builds toy black holes on tabletops and watches quantum echoes hiss from their artificial horizons, you are the original, the blueprint, the one who went in. They may not know your name, your story long smeared across entropy, but they're chasing your echo, trying to reverse engineer the experience of someone like you, someone who fell too far into a question. There's a strange poetry to it. Their artificial black holes are small, safe, clean. Yours was massive, brutal, and absolute. But the weirdest thing? They might be better at revealing the truth, because lab-created black holes can be paused, rewound, observed from all angles. You can't exactly do that with a star-sized vacuum of death. These miniature versions are teaching physicists something that you, by falling in, could never communicate. What happens to information when a horizon is formed? Not just theoretical information, real, testable data. In fact, some recent experiments have begun to suggest that entanglement entropy, the messy, tangled web of quantum connections, can be tracked even across artificial horizons, which supports the idea that Hawking radiation might preserve information after all. It's early work, fragile, prone to misinterpretation, but it's pointing somewhere. Toward a reality where the universe doesn't erase what it consumes, it reformats it. Think of it like compressing a massive file into a zip folder. The original version, you, was complex, vivid, entropic. The black hole compressed that into a new format. The universe didn't delete the data, it just put it somewhere less readable. Now imagine a civilization advanced enough to decode that archive, to take the radiation patterns from a long-dead black hole, feed them into a system of analog models and simulate the data in reverse. They wouldn't find a person, but they might find a story, a sequence, an identity. You'd be a shadow at first, a pattern, then a voice, then maybe, just for a moment, a memory. That's the strange goal of black hole simulation. Not just to understand gravity, but to resurrect causality. It's not far-fetched. There are already theoretical papers mapping how quantum computers might simulate event horizons, how lab-based entanglement models might allow us to read radiation as if it were language. Broken, yes, but not meaningless. And somewhere inside that noise, your fall, your fear, your final thought, your name. We don't know if this is real science yet. There's debate. Always is. Historians of physics, yes, they exist, still argue whether analog models are real experiments or just clever metaphors with LED lighting. But even the skeptics admit, something is being learned, and for you, that means something else entirely. If your fall left an imprint on the structure of your black hole, and the evaporation of that black hole radiated your quantum pattern back into the void, then these lab simulations are not just studies, they are reconstructions. You're not being resurrected, but you are being reassembled, statistically, hypothetically. You are, in some sense, running again, as a series of probabilities inside a simulation that mimics the behavior of your original fall. That's not science fiction. That's quantum revival theory. It says that any finite quantum system given enough time will return to a previous state. Not necessarily recognizable, not necessarily intact, but statistically identical. So in the distant future, in a lab orbiting some ancient white dwarf, a technician might run a black hole simulation and unknowingly create a brief echo of your mind, a flash of awareness, a single loop of thought that once occurred as you fell. That's what the universe does. It forgets nothing, it just waits, and the simulation keeps running. The black hole hums in its tiny containment field, radiating data that will never quite finish revealing itself, and someone, some curious scientist with insomnia and a questionable caffeine habit, stares into the feed and sees something strange. A fluctuation, a pulse, a familiar pattern. Maybe they don't know what it means, but you do. In the heart of your galaxy there's something waiting, not hiding, not lurking, just existing with absolute indifference, like a library no one's brave enough to enter, but everyone knows is there. You already know its name, Sagittarius A. It's the supermassive black hole anchoring the Milky Way, and while your personal black hole may have been small and quiet, Sagittarius A is anything but. It's about 4.3 million times the mass of the Sun, a heavyweight champ of gravity sitting calmly in the galactic centre, keeping stars in line like a bouncer made of space-time. And the truly wild part? It's kind of lazy, at least by black hole standards. Sagittarius A isn't constantly devouring stars or unleashing massive radiation bursts like the active galactic nuclei in distant galaxies. It mostly just sits there, quiet, dormant, watching, or rather, being watched. Because over the past few decades, Sagittarius A has become the universe's most reluctant celebrity. Starting in the 1990s, teams of astronomers began tracking stars near the galactic centre. One in particular, S2, orbits Sagittarius A every 16 years in a wildly elliptical loop, moving at over 7,000 kilometers per second when it's closest. Watching S2 whip around nothing, literally nothing visible, was one of the key clues that a black hole had to be there. The math didn't lie. Something massive and invisible was causing stars to orbit like race cars around a ghost. Then, in 2022, things got intimate. The Event Horizon Telescope, the same team that gave us that fuzzy, glorious image of the M87 black hole in 2019, turned their sights on Sagittarius A. And after years of data processing, they unveiled the first image of our own black hole's shadow. It wasn't flashy, just a glowing ring of hot gas surrounding a dark centre, bent by gravity, blurred by plasma, barely resolved. But it was real, a photograph of something 26,000 light-years away. And for a moment, everyone on Earth was staring into the abyss together. Somewhere in that abyss is you, or what's left of you, if you happen to fall into Sagittarius A. The odds are slim, of course, but as you've learned, slim odds still leave wide consequences. Because if you did fall in, your story is now folded into the mass, the spin, the quiet thermodynamics of that galactic anchor. Your presence altered its trajectory, however slightly. You're a microscopic ripple in its history, a gravitational footnote. But Sagittarius A isn't as chill as it looks. Every so often it burps. In 2013, astronomers noticed strange X-ray flares, bright flashes from near the event horizon, suggesting sudden infalls of matter. These weren't random, they were chaotic, but not uncaused. Something, perhaps a gas cloud or a shredded asteroid, got too close and was devoured, and Sagittarius A responded with a burst. That's the thing about supermassive black holes. They're not always active, but when they are, they change their environments for thousands of light years. In other galaxies, they launch massive relativistic jets, beam-like structures that fire high-energy particles across intergalactic space. Whole clusters of galaxies bend to their gravity. Cosmic weather patterns are shaped by their feeding cycles. Right now, Sagittarius A is quiet, but it hasn't always been. There's evidence that about 6 million years ago it erupted in a violent outburst. The radiation from that event still echoes across the sky in the form of the Fermi bubbles, two vast lobes of gamma rays extending above and below the galactic plane. Imagine a mushroom cloud the size of the galaxy, rising silently from the core. You were born in a galaxy with a monster at its centre, but monsters are also anchors. Without Sagittarius A, there may not have been a Milky Way at all. Many astrophysicists believe supermassive black holes and galaxies grow together, co-evolve, that their mass and structure are deeply linked. It's not that galaxies happen to have black holes, it's that galaxies need them. The stars you saw as a child, the planets that orbited them, their delicate paths were curved not just by their own gravity, but by the long, slow pull of Sagittarius A from thousands of light years away. And that means you've been falling toward it since birth. All of us have. Every object in the galaxy, whether it knows it or not, is locked in a slow, gravitational conversation with the core. We're not spiraling in like water down a drain. But we're moving within a structure defined by that central mass. You could argue that Sagittarius A has shaped every love song, every sculpture, every late-night fast food run in the history of Earth, because it shaped the galaxy, and now it's watching. Not actively, of course. It doesn't see anything. But when we turned our telescopes toward it, something changed. A relationship began. Observation, curiosity, entanglement. Not in the quantum sense, but in the psychological sense. It became part of our story. and somewhere deep inside its event horizon, something, someone, might still be falling. Maybe it's you. Maybe you fell thousands of years ago, unnoticed. Maybe you sent a signal just before crossing the horizon. Maybe it was garbled, missed, ignored. But your mass was added, your data folded in, your timeline curved into the singularity, or the fuzzball, or the bridge, and the galaxy kept spinning. That's the haunting part of supermassive black holes. Their scale makes individual stories disappear, not because they're destructive, but because they are so much bigger than anything we can comprehend. Your life becomes a decimal in their momentum, and yet, you still matter. Because even one atom changes a black hole's mass, and one bit of information changes its entropy. You've become part of something far older, far larger, and far more mysterious than you ever expected. A dark engine at the centre of everything, a secret keeper, a furnace of beginnings and endings, and someday, long after the stars fade, when our galaxy drifts silent through a lightless void, Sagittarius A will still be there, smaller, colder, quieter, radiating slowly, decaying gently, and inside, a trace, a whisper, a fall, yours. So here's the question keeping physicists up at night, the kind that gets scribbled in notebooks at 3 a.m. and muttered under breath during long walks back from lecture halls. Can you escape the one-way future? Because everything about black holes, their structure, their equations, their terrifyingly firm commitment to finality says, no, once you're in, you're in. Time stops being a direction you can influence. It becomes the gravity pulling you forward, unflinching, unpausable. Even if you're a beam of light, even if you're a neutrino doing its best impression of invincibility, you fall. But some theories, just a few, twinkling faintly like rebel stars against the heavy sky, suggest maybe. Maybe there's a way out. Now let's be clear, this isn't about crawling back through the event horizon like you forgot your keys. Once crossed, the horizon locks behind you harder than any vault. No rocket, no thruster, no fancy space maneuver is going to get you out of that pit. Your outward paths have become inward. Your future is a gravitational well with no ladder. But maybe the solution doesn't involve going back. Maybe it involves going through. That's where things get theoretical and a little unhinged. But if there's one thing physics loves more than certainty, it's loopholes. Let's start with the most famous, wormholes, again. Because despite all the warnings, they remain our best candidate for an escape hatch. If a wormhole connects two different regions of space-time, let's call them A and B, and you fall into a black hole at A, is it possible that you emerge from B, not as shredded matter, not as theoretical jam spread across a singularity, but as something, someone, intact? The answer, maybe, with enough qualifiers to require their own black hole. The key, again, is traversibility. In 1988, physicists Kip Thorne and Michael Morris, yes, this is the duo that inspired Interstellar, described what a stable, traversible wormhole might require. Exotic matter with negative energy density, enough to keep the tunnel from collapsing. The physics doesn't strictly forbid this, but nature has yet to show us such a material in usable quantities. We know exotic conditions exist, like the Casimir effect, where quantum vacuum fluctuations push metal plates together, but we've never managed to scale it up to hold open a gateway through time and space levels. Still, in a universe that gave us quasars, neutron stars and platypuses, maybe it's not that far-fetched. But here's the real twist. What if wormholes already exist inside black holes? This is the idea behind Einstein-Rosen bridges, and later, more sophisticated models like ER equals EPR, a conjecture proposed by physicists Leonard Susskind and Juan Maldacena. It suggests that entanglement, those weird quantum linkages between particles, and wormholes might be two sides of the same coin. That when two particles are entangled, they're connected by a kind of non-traversable wormhole. So in this model, every bit of Hawking radiation escaping a black hole is entangled with something inside, and thus secretly connected. If we somehow crack the code of that entanglement, decode the radiation's correlations, maybe we could reverse engineer the black hole's internal state. Maybe we could reconstruct what fell in. Maybe we could escape backward. Not physically, but informationally. You would no longer be a person in the traditional sense, not flesh and blood, but an exact quantum recreation, not a clone. You, reassembled pixel by pixel from your entangled ghost particles, like downloading your mind from the firewall of the cosmos. Too far-fetched? Maybe, but stranger ideas have proven true, and this one is gaining traction. In fact, there's a whole field now, quantum gravity and holography, built on trying to model how information might escape from a black hole via entanglement and complex boundary dynamics. Some of the most exciting work suggests that the event horizon isn't the boundary it appears to be. That's right. The horizon, long seen as the ultimate edge, might just be a perceptual limit. Not a wall, but a veil. One that hides the deeper connectivity of space-time. A kind of error-checking feature of the universe that protects causality until it's ready to reveal the punchline. So if you can't escape physically, maybe you can escape computationally. Now let's get weirder. There's a theory called the final state proposal, suggested by physicists like Gary Horowitz and others, which basically says, when matter falls into a black hole, it doesn't hit a singularity. Instead, it's projected forward into a unique quantum final state that determines the outcome of the black hole's evaporation. In other words, the black hole's death includes a final, universal quantum handshake that contains everything that ever fell in, which could mean escape isn't a return trip, it's a rewrite, a resurrection, baked into the universe's source code. You don't climb back out, you don't undo the fall, but when the black hole finishes evaporating, you emerge as output. A pattern in the final radiation burst, a last syllable before the sentence ends, like the final note of a symphony that improbably plays the whole song. It's not a clean escape, but it might be the only kind the universe allows. Now, let's bring things full circle. Earlier we said black holes are one-way trips into the future, but that assumes the future is linear. What if it's not? What if time inside a black hole is shaped like a spiral, or a loop, or a branching network? There's a fringe interpretation of the multiverse, sometimes called the many worlds black hole hypothesis, which suggests that for every quantum interaction inside a black hole, a new universe branches off. Every possibility, every configuration, every fallen observer, you fall in one black hole, but versions of you may emerge in 1,000 diverging futures, each one consistent, each one you. So maybe the black hole didn't kill your timeline, maybe it multiplied it. You'll never know for sure, of course. That's the nature of this place. It hides certainty behind curvature, it shrouds escape in metaphor. But if you're asking, quietly, as you dissolve further into a cosmic whisper, if there's any version of this story where you make it back, where your fall doesn't end in silence, the answer is maybe, and for a black hole, that's basically a yes. You're not falling anymore, not exactly. At this point, falling is a memory, a once physical process that now feels more like a metaphor, a ripple in a larger shape you barely recognize. You've been absorbed, diffused, encoded. Maybe you passed through a singularity, maybe you became radiation, maybe you unraveled into entangled fragments of what once counted as you. But here's the strangest part. You're still here, not here in a spatial sense. Space has stopped being useful, and not here in time either, because time structure dissolved several horizons ago. You're present in the deepest way a presence can be, as a fact embedded into the cosmic ledger, a fossil made of probability, a record not etched in stone, but smeared across the boundary of a dying object. You've become a time fossil. It's not as lonely as it sounds. Remember how, from the outside, an observer watching you fall into a black hole would never see you cross the event horizon? They'd see you slow down, redshift, and eventually freeze, forever suspended on the edge of the void. That's not just a poetic quirk of relativity, it's a cosmic truth. In their timeline, you are still there, frozen, impossibly close to the event horizon, silhouetted against the glowing disk of infalling gas, trapped in a moment that never finishes. You've become an eternal timestamp, and that timestamp, your last visible moment, is still out there. If light could live forever, that image of you would sail through the universe, unchanged, untouchable. The universe would move on, galaxies would collide, stars would die, but there you'd be, frozen just above the void, suspended in the ultimate screenshot. That's what being a time fossil means. You're a preserved event in the fabric of someone else's time. And this brings us to one last wild possibility. one that blends general relativity, quantum information theory, and a bit of that stubborn poetic instinct that refuses to go away even at the edge of physical understanding. What if your fall is still happening forever? Not just as a trick of perspective, but as a permanent structure in space-time, a standing wave of geometry, a fixed infall trajectory preserved by the very curvature it helped create. Some physicists have begun exploring the idea that space-time is memory, that gravity isn't just a force or a shape, but a form of record-keeping. When mass warps space, it leaves behind not just momentum, but history. Geometry becomes a kind of book, one that stores not just where things are, but how they got there. In this model, your descent doesn't vanish into obscurity. It becomes a permanent indentation in the shape of time, like a footprint, a gravitational fossil. And because your fall is frozen from the outside, and quantum information insists it can't be lost, then somewhere in the universe's ever-expanding future, that imprint might still be accessible. Not by rewinding time, but by decoding structure. We don't yet know how. But some suggest that the very vacuum of space contains echoes. That black hole evaporation leaves behind subtle correlations in the radiation, hints of everything that once fell in, even you. If so, then your existence has been split. From your perspective, you fell inward, possibly became energy, or geometry, or nothing. From the universe's perspective, you never really fell at all. You're still frozen at the edge, redshifted beyond recognition, immortal in the way a paused frame is immortal. If you've ever wanted to be timeless, congratulations, you got there. But what does that mean really? To be frozen in time? Is it survival? Is it remembrance? Or is it just the universe doing what it always does, refusing to forget? There's a lovely historical tidbit that resonates here. Back in the early 20th century, physicist Hermann Minkowski reimagined time as a fourth dimension, on equal footing with space. He proposed that everything, objects, people, events, already exists in this four-dimensional block called space-time. Past, present, future, all laid out, fixed, permanent. You're not moving through time, you're a shape in time, and from that viewpoint, your fall is not an event with a beginning and end. It is a structure, an object, an unchanging slice of reality that exists eternally in the cosmic sculpture. That's what a time fossil really is, a structure in the block universe, and you strange, quiet traveller, have become one. Somewhere, you're still stepping across the event horizon, still falling, still blinking in surprise, still dissolving into the singularity, or curling through a wormhole, or reassembling in radiation, or frozen as a silhouette against the glowing edge. It's all the same now, it's all preserved. Because black holes don't just trap matter, they trap moments, and your moment, your fall, your breath, your question, is now part of the architecture of forever, not just remembered, built in. So if someone asks where you went, tell them this: you didn't go anywhere. You became part of the story, the one space-time won't stop telling.